Dear students, in this lecture we will discuss the introduction of discrete Fourier transform. So discrete Fourier transform is basically again the Fourier transform of the discrete sequence. Now how this Fourier transform of a discrete sequence is different from the discrete time Fourier transform DTFT, right? So now let us consider one discrete time signal, which is, let us say, xn. So xn is a discrete time signal, right? The Fourier transform of this now what will be the Fourier transform now is given by, so it is given by x omega is equal to summation from n is equal to minus infinity to infinity xn exponential minus j omega n. Now let us say this is some equation number 1, for example. Now what is wrong with this equation? Now before that, we will take now this equation 1 is known as DTFT. Now what is DTFT? DTFT is the full form of discrete time Fourier transform, right? So it is discrete time Fourier transform. Now my question is, what is wrong with equation 1? So the problem here is that if you see the sequence xn, xn is a discrete sequence. It is a discrete sequence. Now discrete sequence means a sequence which exists at some specific uh, points, right? Now if you see this equation 1, this omega, so omega ranges from either 0 to 2 pi or minus pi to pi, right? So this is the range for which your omega will work. But if you come here, you will see that the n, it is extending from minus infinity to infinity. Now the problem occurs when you try to process this through a computer. How? Now from equation 1, if you have clearly observed the equation 1, so in equation 1 your n is basically extending from minus infinity to infinity. though your xn is a discrete sequence, but the x omega is a sort of continuous, right? And it is vast because of the range of summation, which is from minus infinity to infinite, right? Now our computer systems, basically they understand, okay, computers understand digital signals, right? Or you can say digital information. Okay, means something which is discrete in time as well as in amplitude, right? So what basically has been done now, this was a problem which was associated with DTFT, discrete time Fourier transform. Okay, now this problem can be sorted out if we make this range, that is n, finite. Okay, if we make it finite, instead of taking it in as infinite, we can take it as finite. So in that case it would become easy for us to compute it through computer. Okay, now what is DFT then? What is DFT? So basically DFT stands for discrete Fourier transform. Now what is this then? This is DFT is the abbreviation basically. Now is when the Fourier transform is calculated at only discrete points. That means when you calculate the Fourier transform of any sequence at discrete points, then it becomes discrete Fourier transform. It does not remain DTFT. Now, how to get the Fourier transform of a sequence at discrete points? Now, the question is how to get this. Okay, and the answer to this is that we can sample. The answer is that we can sample the Fourier transform, right? we can sample the Fourier transform. This is what we can do. Okay. For example, if we have some aperiodic time domain signal, then discrete time Fourier transform is obtained. Okay. That is, DTFT is obtained from some aperiodic, uh, what do you say, aperiodic uh, time domain signal, right? Aperiodic time domain signal. So from this we can have DTFT, but DTFT is continuous in nature, as we already discussed in previous slide, that the range of summation is from minus infinity to infinity. Then a finite range sequence is obtained by extracting a particular portion of such infinite sequence. Now, what do we do? Since DTFT ranges from minus infinite to infinite, so to get some finite or to extract, we can also say, or to extract some finite, sorry, uh, sequence. Okay, so what we do is we extract a particular portion of such infinite sequence. Okay, we extract some finite, a little bit of that. Okay, and then we take the transform of that particular finite range of that infinite sequence. Fine. Because x omega is a continuous signal, that means it is some discrete with respect to time, but it not discrete with respect to amplitude, kind of continuous signal only. Okay, now how do we get the discrete signal, from of this particular x omega? Okay, how will we obtain the discrete signal of x omega? Answer is, what is the answer to this? Answer is by sampling x omega. We will sample x omega, and by sampling x omega we can find out the discrete signal of this x omega, which is continuous in nature. Means x omega is continuous in nature, but we can obtain some discrete signal out of this. Okay, now we call this process, or we can say not process, basically we call uh, you know uh, this type of sequence as windowed sequence. Okay, So it is a windowed sequence. It is not continuous in nature. It is just a part of that continuous or infinite sequence, right? It is that just that part only. Okay. Uh, Now the nature of this windowed sequence is that it is periodic in nature. So it is periodic. It is periodic in nature, right? That also we can discuss how it is periodic. Now, so this is what DFT is basically. Okay. Now this is a periodic sequence, and we can obtain the periodic extension of this particular signal. And this periodic extension, now this periodic extension in frequency domain is called as DFT. Now what we have done, I'll repeat everything. We have DTFT of some discrete time sequence, or a discrete sequence basically, and that DTFT ranges from minus infinity to infinity, and it is quite impossible and difficult, you can say impossible, to compute such infinite range through computers. So what do? We make that range finite, and then we can make computation of that particular finite range of the sequence. Now to get that finite range of the sequence, what do? We sample the DTFT, and through that sampling we will get certain portion of the sequence, and that certain portion of the infinite sequence obtained through sampling of x omega is known as windowed sequence, and windowed sequence is periodic in nature. So we can say that this periodic extension of the sequence in frequency domain is known as DFT. Okay. Now then, how to get, now my question is how to get, how we will obtain the original sequence. Which was what the original sequence? Xn. Now how will you obtain this Xn? And the answer to this is, what is the answer? Answer is IDFT, which is known as inverse DFT, inverse discrete time, discrete Fourier transform. So we will take the inverse of the discrete Fourier transform, and by using that we can easily find out the original sequence Xn. Now let us understand this graphically. For example, we have a sequence. We have a sequence which is Xn, and then we have it is, let us say, existing at some -1 and then 1 and then this is 0. So at -1 it is like this, it has certain amplitude, and then thereafter it is like, let us say, 0, till some infinite, a particular range. So it is like this. So this is one sequence. So now what you will do, this is you'll get the DTFT of this one. Okay, so you'll get the DTFT, and it is vice versa also, inverse also, so you can get the original sequence, right? Now what will be the DTFT x omega will look like this. So this is x omega, which is DTFT of this one. So it would look like this. So it is like this. no, like this. Okay, so this is your omega, and this is, let us say, 2 pi, and then this is, let us say, pi, and then this is 0. Okay, so this is the DTFT of xn. So we'll write x omega is DTFT of xn. Now we will sample this one. We'll apply sampling on this DTFT, and what will we get? We'll get the discrete time sequence, discrete time signal. How? Like this, which exists for certain samples only. So it would be, means, what are you doing? You are basically sampling this part, and you are, since sampling this one, so after sampling this DTFT, which is quite continuous in nature, you'll get something like this, like this. So what is this? What is this? This is what we call as the sampled signal. For example, this is we have the axis here, and this is nothing but xk, and this is the sampled signal, right? It is sampled. Now, because it is sampled, so this is what we have been talking about, that this is how we can get the discrete time signal. Now you can apply IDFT here. By applying IDFT, you can easily get the original sequence. Okay, so you'll easily get x bar n, let us say. So this is the recovered original sequence, right? So it would be like this, and then for n point we'll have like this. So we'll see why it is so through numerical examples also. Okay, so this is n here, and this is not n, so it is something which we call as n and minus n. So it becomes finite now. This is finite, right? So what we have done, we have taken a discrete time sequence xn, we have obtained its DTFT. From DTFT, what we'll do, we'll sample DTFT to get the sampled signal, which is discrete time signal basically, and uh, by applying the inverse of DFT on this, we will get the original xn. Sorry. So from this whole discussion, we can define DFT as, so how will we define DFT? DFT as, like, write the definition. It is a finite duration. So it is a finite duration because we have obtained it from an infinite duration signal. Finite duration frequency sequence which is obtained by sampling one period of Fourier transform. Right? Now, the sampling is done because we must know how the sampling has to be done. because we are talking about only one thing, that we have a discrete time sequence, we have taken its dtft is continuous in nature, it extends from minus infinity to infinity, it is quite difficult or impossible to compute this through computer. So what we do, we make this sequence finite. How to make the sequence finite? We will extract some portion of that infinite sequence, and that extracted portion of the infinite sequence is the finite sequence, which is also known as windowed sequence. Okay, windowed sequence is periodic in nature, right? Then how to get this sampled sequence? We'll take dtft, we'll sample it, and we'll get the sampled sequence. Now when we sample a sequence, so how do we sample? We call this process as sampling process. Now when we are applying sampling process, so this sampling is basically done at n equally spaced points, right, over the period which is extending from omega is equal to 0 to 2 pi, right? Now let us come to the mathematical expression of dft. So mathematically, dft can be expressed as, so we'll write here, we'll bracket it, and we'll write here, mathematically dft can be expressed as, how will we express? Because it is a sequenced signal, so it would be xk. Instead of taking x omega as we have taken in dtft, we will take xk here, which is equal to summation n is equal to 0 to n minus 1. Now you can see that this summation part is basically now finite. It is not infinite now, it is finite, right? Then summation of xn and e raised to the power minus j 2 pi k n divided by n. So this is some equation number 2, or whatever you want to take it as. Now this is the expression where we can say that k basically, so k here is very important. It is, what is k here? K is sample basically. So it is samples, right? So k can, you know, sorry. Okay. So k can be equal to 0 or 1 or 2 or up to n minus 1. This is the range for k, means the samples. Now, because what we have done here, if you have noticed, so xk is equal to, because xk is equal to summation n is equal to 0 to n minus 1 of xn, which into e raised to power minus j 2 pi k n divided by n. So we have n here. Now what is this n? This is the points basically. So these are the points. Now because uh, the summation, or we can say the finite summation, because it is finite summation now. Summation of the given xn has been taken for n points, right? So we'll say that this is n point DFT. It is n point DFT, right? Now, okay, so this is some equation number, let us say 1, for example, or 2, in fact. So if we have to obtain, what? Now, if we have to obtain the original sequence xn from equation 2, what we will do? What we will do? We will, what we will do? We will take the inverse DFT of equation 2, right? This is what. So it is given by, if you calculate this one, so it is given by x n is equal to 1 by n summation k is equal to 0 to n minus 1 and xk, a sample sequence, e j 2 pi k n divided by n. So this is, let us say, 3. Okay. Now here n is equal to 0, 1, 2 up to n minus 1, and equation 3 is known as n point IDFT, right? Now we can, or not we can, basically we will replace e raised to the power minus j 2 pi upon n, because it is something which is common, by some omega wn, where wn is known as twiddle factor. Okay, so, or we can also write it like this: wn is equal to e minus j 2 pi by n. Now what is the role of twiddle factor? And the answer to this is that twiddle factor plays a very important role in making the computation of DFT easy and fast, right? Now we can also write equation 2 and 3 in terms of twiddle factor, as what will be the equation now? Equation 2 is DFT basically, and equation 3 is IDFT. Okay, so this is like this. Okay, now so xk is equal to, so summation n is equal to 0 to n minus 1 So it is xn, and this is wn and k raised to the power n. So what we have done, we have replaced, because wn is equal to e minus j 2 pi by n, right? So n is equal to 0, 1, 2 up to n minus 1. Similarly, we can represent the IDFT. So this was DFT. Okay. Now similarly, the IDFT can also be represented or expressed in terms of Wn, that is Twiddle factor, right? So this equation will become now, what will be this equation? Xn, because why IDFT is being used? To find out Xn from the DFT. 1 by n summation from k is equal to 0 to n minus 1, and we are taking summation of this, so it is here like this. So this is xk into wn minus kn, right? So this is lattice equation number 4, and this is lattice equation number 5. So now same here, we have k or n, it could be equal to 0, 1, 2 up to n minus 1. So class, now let us find out what is the relationship between DTFT and DFT. Now what is DTFT? So the DTFT is, you can note down if you want this in your notebook. So it is a discrete time Fourier transform, which is mathematically expressed as, so what is the equation for this? The equation is given by x omega is equal to summation n is equal to minus infinite to infinite of xn and into exponential minus j omega n. So this is, let us say, what was the equation number 5? So it is, let us say, equation number 6. Okay. So the omega ranges from minus pi to pi or 0 to 2 pi. So that means it would be 2 pi anyhow, right? One cycle, 360 degrees. Okay. Now let us come to the DFT part. DFT is obtained by sampling one cycle of the Fourier transform, right? This is what we have discussed. So DFT of xn is given by, so it is given by, the equation will be, what will be the equation? Equation is xk is equal to summation from n is equal to 0 to n minus 1 xn e minus j 2 pi k n by n. So this is, let us say, 7. Now if we substitute omega is equal to 2 pi k n in x omega, we get that your xk is equal to x omega at omega is equal to 2 pi k n. So this is, let us say, 8. So we can conclude here that on comparing DFT and DTFT, sorry, together we have certain observations or observations, right? And these observations are, for example, 1. So it is the continuous frequency spectrum x omega is replaced by discrete Fourier spectrum xk, right? And the second point could be like infinite summation so infinite summation in DTFT is replaced by finite summation in DFT. And the third is so what we have here, the continuous frequency variable is replaced by a finite number of frequencies located at 2 pi k by n ts, where ts is sampling time. So this was all about today's class, guys. Thank you so much.